So good morning, everyone. This is Pierpaolo Lento from Truesense, a company specializing in ultra-wideband sensors and software and partner of Arduino. So today we will be discussing about the implementation of ultra-wideband technology on the Arduino platform. Very first thing, a short reminder about ultra-wideband, because it's a technology that many of us have in their pockets, but very few know about it. Maybe you have heard of the AirTag, or you have an iPhone, or you have a Samsung Galaxy. These devices, they are all enabled with the ultra-wideband technology. And it's normally used mainly for finding assets in the consumer world. But in reality, the applications that you can implement are many, and they cover basically all of the industries known as of today. And in fact, you can apply these to use cases like asset tracking for indoor navigation, safety by proximity, so you get too close to a machine, the machine stops, a dangerous machine, and smart access, so you get close to a door, to a gate, and it will magically open with basically no call to action. You don't touch your phone, you don't do anything, like in the cartoons. Why ultra-wideband is good for positioning? It's mainly because of the resolution that you can get. I mean, we have been hearing in the past about localization systems implemented with Wi-Fi or via BLE beacons, but they have a big flow. The resolution is in the order of meters, while in the case of ultra-wideband, we're talking about a resolution of ±5 centimeters and 3 degrees in the measurement of angle, because it does not only measure the distance, it can measure also the angle of arrival of multiple devices in front of it. So I will skip the numbers, you will find this in the presentation. Why so? Because it's completely different the way the radio frequency is managed with the ultra-wideband. Other technologies, normally they use some kind of modulation. In this case, I'm making an example of FSK modulation, so it's the classic sinusoid. While in ultra-wideband, what you do is you use pulses, like a telegraph, okay? And this gives a couple of advantages. Like in the telegraph, even if you have big noise in the environment, you will still be able to perceive this pulse. And the second thing, which doesn't appear in this slide, but it's evident in the next, which is more like a real use case scenario, where you have some noise in the RF. Now, suppose that you want to measure the moment when a specific signal is arriving at the receiver, right? With the pulse, and if you consider the red line as the threshold of arrival of that signal, with the ultra-wideband, thanks to the fact that it is a peak, you have just one single point where the threshold is crossing the signal. While, and of course that's zoomed in the sinusoid, if you look at there, you will see the red line, it goes through the signal at least 3 times, just because of the noise. So which is the real moment the wave has arrived? Very difficult to tell, and that's why you don't get a good level of precision in the ranging, in the measurement. As I said before, ultra-wideband is not a new technology, it's here since many years. Maybe some of you have been hearing about ultra-wideband, especially used in the industrial world, in the logistics world for real-time location systems. But so far, all these systems were custom, they were proprietary. So whichever system you were applying, you were falling into a single vendor lock-in issue. But now the situation is different. There is a standard, finally, which is establishing, of course, all the, let's say, physical characteristics of implementation, but also the logical part of the protocol, including all the parts related to security. So the protocol is designed with security in mind already. So you're not going to get spoofing, man in the middle of attacks, etc. It's future-proof, and it's already built with many different use cases in mind. What we did with Arduino, I let Francesco explain.
I can tell something here. So, as Gianpaolo said, now the situation is different. FIRA standardized this new technology, and so we decided to enter it. And we decided to enter it with a kit that we called ultra-wideband kit, which is made up by two components. The first one, this one, we called it Arduino Stella. And basically, it is like an Apple AirTag, but in a form of a development board. So you can use it, you can customize it from a software perspective, and partially also from an hardware perspective with your functionality. And this includes the ultra-wideband transceiver. There is a microcontroller on it, so you can program it with a classic Arduino sketch. And then you have things like IMU, buzzers, LED, buttons, so things that you may find it useful in your application, and also a quick port that you, as you have seen with the previous presentation from Marta, it's an expansion port that allows to connect this board with our line of Modulino breakout ports. So you can add additional sensors and actuators that are not already present in the board. So you can use it for prototypation and also for building your final system. The second element is a shield. A shield is a component of our Arduino Pro line of system on modules called Portenta, and is basically something that's similar to the shield of the classic Arduino Uno family, so something that you can plug on a Portenta SOM, which is a quite powerful microcontroller, for adding additional functionality. In this case, we put there another ultra-wideband transceiver. So you can use the Portenta plus the ultra-wideband shield as a static anchor. I don't know. It's, I think, the right term in the ultra-wideband terminology, populating a room with them, and then you can use the Stella like mobile devices. So like a tag, you can tag equipment, you can tag person, you can track AGV. There are very lot of application. So this is the way in which we want to address this market, and this is the hardware set that we provide for the user for simplifying their application.
Okay, now we go into something more technical, so as we can explain which kind of use cases are supported by the technology, by explaining which configurations you can use for the different devices. So you have these 4 cases now. We go through them one by one, okay? We start with the single-sided two-way ranging. We basically have 2 devices. It could be 2 Stella tags, or it could be 1 Stella and 1 shield, which are exchanging messages containing timestamps. And then by comparing these timestamps and the time it takes for this signal to cross the air and arrive from one device to the other, you can basically already calculate the time of flight. And of course, based on the time of flight, you get the distance, because it's simply the speed of light. Unfortunately, devices, they have clocks. Clocks are based on quartzes, but quartzes sometimes they are not exactly the same. And since we're talking signals that are traveling for maybe picoseconds, of course, a skewing in the clock, it will be a problem, which you need to compensate, which in this method, we are not able to compensate. The other method that is closing this issue is the double-sided two-way ranging, where you have more messages exchanged, and by this you can basically calculate also which is the clock skew, and so you get a better precision, at the cost of the fact that for getting a single measurement, you are exchanging more messages, and so this method, it will be a little bit more power hungry compared to the single-sided two-way ranging. Which is the limit of this? So first thing, which is the application? You have seen 2 devices, it could be more devices, but basically with 2 devices you are implementing proximity application. You know which is the distance and the angle between these 2 devices. So again, it could be for opening the doors, opening gates, or safety applications, etc. The problem we already mentioned partially. It has a high rate of occupancy of the RF spectrum, because for each measurement you're basically exchanging 5 or 6 messages, depending on some specifics of the configuration, and which also increases with the refresh rate that you want to get. You can measure hundreds of times per second, not always needed, but indeed this is the most power-hungry configuration that you can get. At the same time, is the only one that today is available on mobile phones. I'm talking all the iPhones starting Series 11, also the Apple Watch starting Series 8, all Google Pixels, Galaxy S, the new Motorola, and more is coming because Snapdragon, the new Snapdragon from Qualcomm, will be including ultra-wideband also for the mid-range phones. So this will contribute even further to making this technology available to the large public. Let's go into something more complex, the so-called time difference of arrival method. This is a little bit more convoluted, because what you need is basically a series of anchors, typically around the borders of the space that you want to monitor, where you want to track assets or people or goods or whatever. These anchors are configured to listen to tags, so for example the Stella tags, moving within the environment, battery power, whatever. There is also some, again, due to the clock skews, there is some synchronization anchor, the one in red, and basically all these anchors are then connected to a central server that is basically doing all the, let's say, triangulation operation that will let you calculate the absolute position of the tags within the infrastructure. Why so? Because this is a much more scalable configuration compared to the other. I could have been doing everything with the two-way ranging, but then I have a limitation. Maybe some of you, I skipped it, but some of you may have noticed, you may have maximum 40 devices per anchor in two-way ranging mode, which is not the case for this. In this case, the tag is not really exchanging messages back and forth with the anchors. It's just sending blinks. It's just, turning on the radio, send a 2 nanosecond blink, and then shut down the radio. The blink, it will contain, again, an identifier of the tag and a timestamp. Different anchors in the infrastructure, they will receive this same blink at a slightly different time based on the distance. And based on this difference of distances, so that's why time difference of arrival, you can basically do the triangulation and calculate the absolute position, not only the relative position of the tag itself. So compare to the previous method, of course, this is only sending one message, no responses, no else. So you save a lot of bandwidth over the air, which means you can have a much higher density, a much higher population of tags that you can track. And at the same time, the power consumption is much less because you're not sending 6 messages, you're sending just one, and you're not even waiting to receive the response. So you save a lot of radio time. Typical application is the logistics industries, big warehouses. You want to track forklifts, you want to track tools, you want to track assets, you want to track people. That's the best application to use. There is another one, which is basically the opposite of what we have just seen. It's called, in fact, the Downlink TDOA. In this configuration, you still have an infrastructure of anchors, but I guess you already noticed there is no servers and no connection via IP or via some back network that talks to servers and so on. Why? Because in this configuration, we have exactly the opposite as before. The tag, it never transmits. It's configured to listen only. And the anchors are then configured to do some kind of round-robin ranging between all of them. The tag can understand all these messages, and based on the timestamps of these messages, is able to calculate its own position. Why is this important? Because in some applications you really need very, very low latency. I'm talking autonomous vehicles, basically. Drones or whatever. Whatever needs to be tracked, knows its own position in the real time because it needs to take immediate decisions. This doesn't come for free, of course. The radio is always on. It means this method is consuming more power, okay? But you have a big advantage. You basically consuming always the same bandwidth over the air. So this system, it can scale forever, okay? You can add as many tags as you want because they never transmit. They never take more bandwidth. So it's a very good application also for indoor navigation. It's a news of these days where Apple with iOS 26, they just introduced the possibility to use this type of configuration on the iPhone. So we do expect many applications for indoor navigation to be available on the phones. And the nice thing is this is done in full privacy because there is no server. There is nothing that is tracking your position. Only your own phone knows it. And so it's safe, you know, for many, many different use cases. So to summarize, very quickly, two-way ranging. We talk scalability, power consumption, network architecture. Scalability, I think we all understood it's very low. Power consumption is high. But you have basically no infrastructure needed. It's good for, again, proximity applications mainly. TDOA, it scales very well. I mean, you can track really thousands of objects in real time without major issues. The power consumption is very low. A tag that is doing this operation running on a CR2032 battery, the typical coin cell battery, it will go ahead for 3 months operating 24/7 at 5 updates per second. Of course, you can do optimizations. There is a reason why we have an IMU on the Stella. Basically, we use it to stop the transmission when the thing is not moving, or maybe reduce the number of updates per second. So it can go ahead for months, really, even years, depending on how many updates you want, which is your refresh rate. And then the Downlink TDOA, super high scalability, but very high power consumption, with a simpler infrastructure compared to the TDOA method, which on top, it requires some out-of-band method to talk to servers that do the triangulation. Well, I don't know why the slide is like this, but anyway, of course, we did the hardware, but the hardware alone is never enough. You need software, okay? I heard the colleague from Silicon Labs before showing like 60 lines of code to implement a full matter device. The same philosophy applies to the libraries we created for managing ultra-wideband sessions on the Stella and on the Shield. The examples are already available. There are more to come on the GitHub, and they support already all the modes that we have been describing today. You may have noticed we put some accents also on the availability of ultra-wideband on mobile phones. The reality is, if you try to look at the documentation, it's not going to be easy. If you try to look, for example, it's even harder. So we decided also to create some reference applications for both iOS and Android. Open source, you can go on our GitHub repository, download the source code, build them by yourself. So it should give really a kickstart to enablement of maybe pre-existing applications that we are using in the past, BLE or else, to make them really automated. No call to action. That's very important. You approach the door with your phone in the pocket. You don't need to take it out, launch the app, select the door you want to open, and then open it. You just keep it in your pocket, approach the door will open. You will see this soon on the market. Finally, what is coming is not there yet. A real-time location system based on TDOA, where we use the Stella and the UWB shield for the anchors. This will be made also open source and made available very soon. That's it. These are the links. If you're interested, you can go and check. Of course, there is also plenty of documentation on the Arduino website for the libraries. Thank you. If any questions?